Welcome to section 2.2, which covers separable equations. So now that we've had the background, some of the vocabulary in terms of what is a differential equation, what is an initial value problem, and we've looked at some of the initial modeling, it's time for us to actually start solving equations. So the first type of solving that we're going to cover is separation, and this is something that you have seen a little bit in Calc BC, but we're going to add on to it. So starting at the top, if g of x is a continuous function, then the differential equation dy dx equals g of x can be solved by integration. And you did this, like I said, in Calc BC. So we kept y's on one side, we kept x on the other. So on the right side, I'm going to end up with g of x dx. Then I'm going to integrate. The integral of dy is just y. The integral of g of x is capital G of x plus c, where capital G of x is the antiderivative of little g of x. Okay, so now we're going to do example 1, and then we'll move on to adding on to this. Okay, so we can see in this case, we can get all the x's on the same side. So I'm going to have dy is equal to secant x tangent x, subtract sine squared of x, all of that dx. Y is on one side, x is on the other, so I can now integrate. I'm going to get y equals, integrating secant x tangent x gives me just secant x. Then we got to think about how do we integrate sine squared of x. Well, sine squared of x is the same as 1/2, subtract 1/2 cosine of 2x. But then we have to remember we also have this negative. So that's really what we're integrating. So when we integrate what we have in red, that gives us negative 1/2 x, add 1/4 sine of 2x plus c. Okay, so that you've seen before. What we're going to look at now is that specific case being equal to g of x. That is one particular case of this more general equation. dy dx equals a function of x and a function of y. So what we can do then, when we're solving that, get the x's and the y's together. So we would end up with h of y dy equals g of x dx. X is on one side, y is on the other. When we integrate then, we're going to have h of y equals g of x plus c, where both capital H, capital G are antiderivatives. So note, you really only need to put one c here. Yes, you're going to get a c and a c, but really it's just one constant, so this is a neater way to write it. And just a note, oftentimes we want to look for an implicit, or an explicit solution where we have y equals. We might not be able to find that. So we may not be able to find explicit solution for y. So that is really what this video is all going to be about, is at this point, examples of solving by separation. We're going to review quite a few things that might be buried a little bit deeper in your brain from Calcs 1 and 2, so some things that hopefully we can review and bring back to the surface. Okay, so example 2, we see solve dy dx equals that equation. The first thing that you're going to be asking yourself is, can I get y's together and can I get x's together? Yes, you can. So we're going to get y squared dy, and we're going to have x subtract 2 dx. At this point, you're going to integrate. So we end up with 1/3 y cubed is equal to 1/2 x squared, subtract 2x plus c. Okay, so this is an implicit solution. So what we're going to want to do is solve for y if we can, which we can if we multiply by 3 and then take the cube root. We're going to get y equals the cube root of 3/2 x squared, subtract 6x plus c. Now here's where we need to be a little careful. If I call this C1, let's note that these are not the same c's. So what we did is we took C1, we multiplied it by 3. So this really then is C2, which is 3 times C1. So you're going to need to be careful with your notation there. Now, if you want to not even use C2 and you want to write 3C1, you can certainly do that. That's just not normally the way that we do things, just to make it a little bit neater. So that was one. Let's try another one. Okay, so next one is an initial value problem. We have our equation and we also have a condition so that we can find C. Now, what you should be thinking as you're going through these is, why are these separable, right? How would I have known right off the bat to use separation? Because after this video, you're going to learn another method, and then you're going to learn another method. You're going to keep learning methods. And so it's going to be important for you to be able to pick and choose, when do I use separation? When do I have a linear equation? So on and so forth. So separation is a nice way to solve problems. So the first thing I would do is say, can I get my x's and y's alone? And of course, yes, I can. So I end up with 1 add 2y dy is equal to 2x dx. Okay, so I'm going to integrate then. I get y add y squared is equal to x squared add c. Okay, so at this point we have a few different options. We can solve for c. We can solve for y. What I'm going to do is I'm going to start by solving for c. So I end up with 2 squared add c is equal to 0. So my c then is -4. My equation becomes y squared add y is equal to x squared subtract 4. Okay, so at this point we can certainly solve for y. It's going to involve completing the square. So I'm going to have to complete the square for y. So if I take that 1 divided by 2 and square it, I'm going to have to add 1/4 to both sides. So when I do that, I get y add 1/2 quantity squared is equal to x squared subtract 15 over 4. Take a square root. We get y add 1/2 is equal to plus or minus the square root of x squared subtract 15 over 4. Okay, now at this point, do we need the plus or minus? No. If we look back at this initial condition, if we plug in a 2 for x and a 0 for y, so we get 0 plus 1/2 is equal to plus or minus some square root. This side is positive, so it's going to have to be equal to a positive quantity. So we don't need that negative. So keeping that in mind, we get y is equal to -1/2 add the square root of x squared subtract 15 over 4. Okay, quick note for you. We decided to find c before we solved for y. We could have done it the other way. So once we had gotten up to here, we could have completed the square. So we could have completed the square to solve for y first and then found c. I chose to find c first. Okay, so let's take a look at the next example, which is again going to review some techniques of integration that maybe we have forgotten. So in this case, we have dx and dy. We need to figure out, can we get the x and y together? Well, yes, we can. This e to the -y, I'm going to have to get with my y. So I have x sine of x dx is equal to y e to the y dy. Then I'm going to integrate. So at this point, you should be thinking, this is why she chose this problem. We're going to have to do integration by parts. So then if you remember from Calc 3, I don't particularly love integration by parts. And so sometimes we can use what is called tabular integration. And if you remember with tabular, you split your expression into 2. You are differentiating one, and you are integrating the other one. Whatever one you're differentiating has to eventually get down to 0. So I differentiate x down to 0. I'm going to integrate sine of x then, so I get negative cosine of x and negative sine of x. So then we go on a diagonal, and if you remember, we have opposing signs. So adding here, subtracting here. Okay, so on the left side then, we are left with negative x cosine x add sine of x plus c equals. Same thing, we're going to have to do tabular or integration by parts for the y. So we're going to differentiate with respect to y. We're going to integrate. I'm actually going to move this way over to the right to give myself some room. Whatever we're differentiating has to get down to 0. And then e to the y always becomes e to the y. And again, opposing signs. So that will give us y e to the y, subtract e to the y. And that is our answer. We cannot solve for y in this case. We can't get an explicit solution rather. So this is our implicit solution. Okay, we've got one more example to go through. Again, it's going to review some of the techniques that you might have forgotten. And of course, I saved the best one, in other words, the trickiest one for last. So let's jump into this last one. Again, we're given an initial condition, so we're going to have to find C when we get to that point. So first thing I notice, I can get my y's and my x's together. So I have dy over y squared subtract 4 is equal to dx. And that's what I'm looking to integrate. Okay, so the question is, how do we integrate y squared subtract 4? Well, what we're going to have to do is express this in terms of partial fractions. So this is a over y minus 2, add b over y add 2. Okay, so then if I get rid of my denominators, I have 1 is equal to a multiplied by y plus 2 plus b multiplied by y minus 2. When you did this in pre-calc or calc, there were two different ways you could go about it. One is by writing a system, and then another one is by choosing convenient values. I prefer the system method, so I'm going to distribute. Okay, so if I look at my y's, there are 0 y's on the left side, so I get 0 equals a plus b. And then if I look at my constants, I get 1 is equal to 2a subtract 2b. From this top equation, I get a is equal to negative b. If I substitute that in then, I get negative 4b is equal to 1. So b is equal to negative 1/4, and b is a is equal to positive 1/4. Again, if you prefer just choosing convenient values, you can certainly do that. Okay, so now taking our differential equation, what we have is 1/4 over y minus 2, add negative 1/4 over y plus 2, all of that dy is equal to dx. And so now we're going to integrate. We get 1/4 natural log of y subtract 2, subtract 1/4 natural log of y add 2 is equal to x plus c. Okay, on this left side, I can multiply by 4 and then condense those natural logs. So I get the natural log of y subtract 2 over y add 2 is equal to 4x add c. Now in this case, these c's are not the same. So I'm going to call this one c1 and this one c2. So c2 is 4 times c1. Okay, so then apply an e. So we end up with y subtract 2 over y add 2 is equal to e to the 4x add c2. But if we look at that right side, this is really e to the 4x times e to the c2. Well, e to the c2, that's just a constant, right? So I'm going to call this constant now c3. Again, just because it looks nicer, it's a little bit easier to work with. So where that leaves us, we have y subtract 2 over y add 2 is equal to c3 e to the 4x. Okay, so we have two options here. Option 1 is we can solve for c. That's what we did in example 3, I think it was. Or we can solve for y, get y alone, because we definitely can do that. So that's what I'm going to do is I'm going to next look for my explicit solution. So I'm going to solve for y before I solve for c. So I end up with y subtract 2 is equal to y add 2 c3e to the 4x. So if I get my y's together and factor out common terms, so I'm going to do a few steps in one, I'm going to end up with 1 subtract c3e to the 4x. And on the other side, I'll have 2 c3e to the 4x add 2. So finally, for y, I get, factoring out at 2, 1 add c3e to the 4x over 1 subtract c3e to the 4x. Okay, so now we are finally at a point where we can find c3. So our condition is y of 0 is equal to negative 2. So we're going to substitute that in. We get negative 2 is equal to 2. 1 add c3 over 1 subtract c3. So we get negative 1 is equal to 1 add c3 over 1 subtract c3. Okay, so if I multiply by that negative 1, I get negative 1 add c3 is equal to 1 add c3, which gives us negative 1 is equal to 1. Okay, at this point, you should be saying, uh-oh, where do I go from here? Mathematically, everything that we did is correct. So we did not make any mathematical mistakes. Instead, what this tells us is that we're going to have to approach this problem in a little bit of a different way. So what we're going to do is we're going to actually start again. Okay, so our equation was dy dx is equal to y squared subtract 4. Now, one thing you might have noticed initially is that y squared minus 4 is going to factor. Well, what you're going to notice then is that dy dx is equal to 0 for y is equal to 2 or negative 2. And so you might be wondering, why do I care? Well, our condition, y of 0 equals negative 2, occurs at the point 0, negative 2. So what we do with that then is we go back to our equation using these two values that we solved for. So we know that dy dx will be 0 for one of those two values, or maybe both. So we have plus or minus 2, that's our y, is equal to 2 times 1 add c3e to the 4x over 1 subtract c3e to the 4x. And this is what we need to solve. So what we end up with then is 1 equals 1 add c3e to the 4x over 1 subtract c3e to the 4x. And then we get negative 1 is equal to the same fraction. Now, that fraction on the right, this one right here, we already solved that over here on the left. So we know that that's not going to give us a solution. So instead what we're doing is we are solving this one on the left. If we do, we get 1 subtract c3e to the 4x is equal to 1 add c3e to the 4x. So we get c3e to the 4x then equals 0. So c3 has to equal 0 then. So going all the way back to this general solution that we got then, we have y equals 2, 1 plus 0 over 1 subtract 0, which gives us simply y equals 2. So that is our specific solution that comes from the initial condition we were given. So if you remember, this is called a singular solution. That's called a singular solution. So up here in the black box at the top, we have the general family of curves, the general solution. We couldn't easily get to y equals 2 from the work that we had, right? And so we had to think a little bit differently. we had to go back to where is dy dx going to be 0, and then those are the y values that we plugged in. So this doesn't come up very often, but now you have another tool in your pocket if you end up with an initial value problem and you're trying separation and you're running into some walls. But again, this does not happen very often. So at this point, we should have reviewed some of the techniques of integration. And remember, in your mind, you need to keep thinking about, why am I separating? How do I know that this equation is separable? Because soon, starting in the next video, you're going to have to be able to differentiate which method to use. Until next time, thanks for sticking with me.